Stack corruption when changing plaintext, ciphertext, and checktext from globals to locals in C/C++. In C and C++ programming, managing variables and memory allocation is crucial for preventing errors and ensuring program stability. A particularly elusive bug that developers might encounter is stack corruption. This issue can arise when transitioning variables such as plaintext, ciphertext, and checktext from global to local scope. What is stack corruption? Stack corruption occurs when a program inadvertently overwrites memory locations on the stack. This can result in erratic program behavior, crashes, or security vulnerabilities. Common causes include buffer overflows, improper pointer usage, and incorrect array indexing. Why does it happen? When converting plaintext, ciphertext, and checktext from global to local variables, the stack's behavior changes in several ways. Memory allocation differences. Global variables are allocated in a fixed memory segment allocated at the start of the program, whereas local variables are allocated on the stack, which grows and shrinks with function calls and returns. Local variables have limited scope, and their memory is released when the function exits, while global variables persist for the program's lifetime. Stack size limitations. The stack has a limited size, often much smaller than the heap. Large local variables can cause the stack to overflow, leading to stack corruption. Pointer invalidations. If pointers to local variables are retained beyond the function's scope, for example, returned from the function or stored in global structures, accessing those pointers will lead to undefined behavior since the memory they point to is no longer valid. An example with AES and OpenSSL. Imagine we are using OpenSSL to perform AES encryption and decryption. Consider the following scenario where plaintext, ciphertext, and checktext are used within functions. When plaintext, ciphertext, and checktext are defined as local variables, they are placed on the stack. If these arrays are large or if multiple nested functions use significant stack space, the risk of stack overflow increases. In contrast, if these variables were global, they would be placed in a static memory segment, significantly reducing the risk of stack overflow. Debugging stack corruption. When faced with a stack around variable with corrupted error, consider checking buffer sizes. Ensure that your arrays or buffers are not exceeding the stack limits. Memory management practices use dynamic allocation, heap, for large data buffers instead of relying on the stack. Compiler warnings/tools use compiler switches, stack protector for GCC, and tools, valgrind, address sanitizer, that can detect stack corruption. Conclusion. Variable scope changes can significantly impact memory management in C and C++. Moving plaintext, ciphertext, and checktext from global to local scopes can induce stack corruption due to limited stack space and scope-limited memory. Understanding and mitigating these risks ensure robust and secure applications.